The announcement will go from current slide. I hope it'll get there. Had trouble getting there earlier. There we go. Okay, before we get going on the actual math, let me hit the announcements. You all know about the student course evaluations, right? Hopefully you have either done them or are planning to do them. Please get them done before August the 8th, because I won't be here on August the 8th to remind you, okay? So please get those done. Any questions about how to get to them? You understand that? Good. All right, the second thing has to do with my office hours. We have a big, what they call a planning hearing tomorrow, and that's going to be at 1:30 over on the Birmingham West Campus, okay? Which means I'm obviously not going to be here during my office hours tomorrow. I will be here after 10:45. I've got class from 8:30 to 10:45, but then shortly after 10:45, I may be having to leave and go over there. Definitely before 1 o'clock, I've got to leave to go over there. So I don't know what time I'll leave. I'm going to work on as much of this after class as I can today, so I don't have as much to do tomorrow, but there still may be people turning in some stuff tomorrow that I might have to go over there earlier. So anywhere from 11 till 1, I'll be leaving to go over to the Birmingham West Campus, and then once I'm through with that, then I'll be free to do other things, but I won't be coming back here. I've got class over there at 5 o'clock, so I'll just stay over there and work from that campus. Now, Thursday then, we go back to what is listed on my syllabus and locator card and stuff. I'll have office hours available on Thursday from 10:45 until close to 4:15. I think I'll put it on there 4:30. I found that it's hard for me to make it over there in half an hour, so I'm going to leave at 4:15, just in case there's trains, traffic, other issues that get in the way. So I'll leave here at 4:15 and hopefully be there well before 5 o'clock when the class starts. So Thursday will be back to sort of normal. Okay. Then next week we have class Thursday only, and Tuesday only. And in fact, I'll probably curtail class a little bit early so you can work more on your final exam. So we will just see what it There is class on, I'm sorry. Goodness gracious. There is class on Monday, and I'll give you your final exam. Hope if I can get it ready by Wednesday, I'll give it to you Wednesday, but the odds are, the way things are going now, I don't think I'm going to have a chance to do it because I'm going to be tied up probably all day tomorrow on that hearing, so I'm not going to have time to do much. But if I can, I'll have it ready for you on Wednesday. Otherwise, it'll be Monday. I'll give it to you Monday and after class, and then you can get it back to me Tuesday, Wednesday, or Thursday. Now, let me just tell you what my deal is on next Thursday. Again, like this time, I'll be leaving this campus about 4:15 to go over there. So the latest I can get it on this campus is 4:15. If you want to catch me on the Birmingham East Campus, I'll be there until 6:30, probably a little after 6:30. So we'll talk about that next week when I give you your test, where to turn it in. Okay.
Final exam is chapter 14.
Yeah, I don't think we're going to get into 15 at all. I had hoped we would at least scratch the surface there, but I was just looking at what we could skip in 14 to get to 15. There's not a lot. So let's give it our best shot and go from here. Okay. Any questions? Anything we've covered so far, or how we're going to wrap up? Okay. Now, Chapter 14 is still multiple integration. That's what we've been in for a little bit now. And 14.4, is where we're starting today, is center of mass and moments of inertia. Now, we may curtail this a little early and move on, because the main thing I want to hit before we're through is 14.6, which is triple integrals and applications. Okay? And so if we need to move along a little faster, I may, after we got just the bulk of this done, move on to 14.5. So we don't need to get to 14.6 today, but we need to get there before the term's over with. So let's see how we can go here. Any questions before we get going? Okay, 14.4, center of mass, and moments of inertia. Now, I hope you recall, you did centers of mass back in Cal 2, I believe it was, wasn't it? Okay, now we're going to be doing three-dimensional centers of mass. Okay, so our objectives here, to find the mass of a planar lamina using double integral. Okay? Now, I don't know if you remember before, what we meant by a lamina was something with uniform density. So now we're dealing with a planar lamina, and that means, of course, uniform density throughout it. And then we'll find moments of inertia using double integrals. So both of these are applications of the double integrals we've already talked about. So we'll start with mass. Find the mass of a planar lamina using double integral. I skipped something here. Find the center of mass of a planar lamina using double integrals, and find moments of inertia using double integrals. Three different things: total mass, center of mass, and moments of inertia. Okay? So let's deal with mass first. If the lamina, and remember lamina means uniform density, the lamina corresponding to a region R, okay, now this region, you're fixed on the X from A to B, the Y's go from G1 to G2, okay? If the lamina corresponding to the region R, shown in here, has a constant density rho, meaning there's no difference in density here, anywhere along there, the density is constant, lamina of constant density, okay? Then the mass of this lamina is given by the double integral, which is the integral over this region R, that, and you would do the dy's first as you go g2 of x minus g1 of x, and then do the x's, dy's last as you go x equals a to x equals b. Okay? Now they don't show that part here. They just say it's that density, constant density rho, times the area of this, and of course the area of this is the double integral from rho, double integral of r dA. Now, this makes no sense at all to me, why they did this. If rho is a constant density, leave it out here. There's no reason to take it inside the integral here. If it's a constant density, it's there. Now, if that's a variable density, for sure you've got to take it in there. But they're saying it's a constant density, so leave it on the outside. There's no reason to put it inside the double integral. Okay? That I can think of, maybe so. Let's see. If not otherwise stated, a lamina is assumed to have that constant density. We will extend the definition of the term lamina to include thin plates of variable density. So we will do that, and if we do, then the density has to go inside. So that's why they put it inside. Double integrals can be used to find the mass of a lamina of variable density, but then you have to bring the density inside the integral, where the density at xy is given by the density function rho. Same rho that we used before, only this is a function of either x or y, or both x and y. Okay. So here's the definition of a planar lamina of variable density. For constant density, it's this one, and there's no reason to bring it inside the radical. Inside the integral. This one, you have to have it inside there. Okay? If rho is a continuous density function on the lamina corresponding to a plane region R then the mass M of the lamina is given by, the total mass is given by this double integral over R of this density function, rho of xy. Now that could be only a function of x, only a function of y, or a function of both, times dA, whereas your dA will be your, just like we did before, your dx dy or dy dx, whichever happens to work best. Okay, so here's example 1 with no further ado. Find the mass of the triangular lamina with vertices at 0, 0, 0, 3, 0, 3, and 2, 3. Okay, so a triangle there. Given that the density at any xy is 2x plus y. That's your density function. Okay. Now, that's a bit bizarre for this one reason right here. It says a vertex is at 0, 0. That would have no density there. So, what in the world? Do you have a hole there? That part doesn't make a whole lot of sense. Or else it shaves to right there. You have no material there at all. I guess that could happen. It's just rather bizarre. Okay. But this is a math problem, not a physical problem. Okay. Now, let's not do that yet. So find the mass of a triangular lamina with vertices. Okay, so let's go on and let me get my pen set up and draw okay. Okay. So here's your vertices, 0, 0, 0, 3, and 2, 3. So here is your let's see if I can draw it maybe a little better. Okay, that's not very good, but I'll do the best I can with it. Okay. Well, thought it was going to do well, but lost that part. Okay, so here's your triangular lamina with very low density down here, but denser up here and here. So there's your lamina, okay? We want the mass of that triangular lamina with those vertices and that density function. Well, the mass is what we just had. Let's go back and see it. There it is. The double integral from covering R of rho of xy dA. Okay? So that's the double integral across, and this is our region R, times rho of xy dA. Why my D didn't show up, I don't know. Okay. Now, the density function, so the mass is the double integral. I'm going to leave off a little bit here and just write in this. It's the 2x plus y. Okay. Now, here's the thing you have to decide first. What do you want to be your order of integration? Okay? We could do, at the end, the x is going from 0 to 2. Okay? So that's going to be your last integral. X is going from 0 to 2. That means your first integral is going to be going from y. Well, you got to get this formula, this function here. Y is equal to that's how best to say this. So let's say we have our dx's at the end going this way. So our y's are going to be going from y equal this line to y equal that line. And you have to get this line as a function of x. And that's probably not a bad way to do it. Seems just as good as any. So your dA basically is your xy. So let's get this line here as a function of x. We know that this point here, which is 2, 3, is on that, and we know the point 0, 0 is on that line. And that's the y-intercept, by the way. So this line here is y is equal to, the slope is going to be 3 minus 0 over 2 minus 0, so that's 3 halves x. Y-intercept is 0, right? Okay, so there is your, that one. So if we're doing this, our first integration is going to be from y is equal to 3 to y is equal to 3 halves x. So this will be 3 minus 3 halves x, okay? Then that would be your dy, and then, I'm sorry, that's not where you put it. Okay, you put it on the integral here. Your first one is going to be going from 3 halves x up to 3, okay? That's going to be your dy. And then the x's are going from 0 to 2. Okay. Now, again, let's do a quick recount here. Use your density function. That's always in there. Your dA is dy dx or dx dy. Doesn't matter. If we're doing the dy's first, we go from y is equal to 3. That's the upper limit. So from y is equal to 3 halves x up to y is equal to 3. So from 3 halves x to 3, doing the y's this way, and then we're going to sweep our x's from 0 to 2 and do that part. Does that make sense? Okay, that covers the area and everything that you need. So let's do that. M is equal to, we're not going to mess with the x's yet, so leave that 0 to 2. And we'll take the antiderivative of this with respect to y. Okay? So what is that going to be? Antiderivative of that with respect to y. Anybody? Okay, a little louder, I can't quite hear you.
X squared.
No, with respect to y. Don't integrate that, okay. Is what? Say again? 2xy plus y squared over 2. Perfect. Evaluate that from 3 halves x to 3. And then we'll do our dx later. Okay? Now, integral from 0 to 2. Now we're plugging in. Now I sometimes like to write y equal 3 to y equal that. So I remind myself, these values are going in for the y, not for the x. So what would the first one be? When you say again? Okay, 2xy, where y is equal to 3. What would that be? It'd be, did you say 6x? Excellent. Okay, 6x plus, and then 9 over 2. Okay. And here we have 1. Davis, I'm sorry. I keep wanting to call you Warren Davis rather than Davis Warren because that's how you are in the book. Warren is listed first because it's his last name. All right, we evaluated at y is equal to 3. Now let's evaluate at y is equal to 3/2, but it's the minus now. So that will be what? Minus what? 3x squared, isn't it? Because you had an x there and an x there, right? And the 2's canceled out. Okay, next. Oh, wait. I'm sorry. I did the wrong one. No, I did it right. Sorry. Okay. My pen's messed up now. Okay. And there's also a minus here. When you plug this in for that, what does that give you? It's 9/4, isn't it? Wait. Okay. So 9/4 over 2. Second? Okay. The y is 3/2 x, and you're going to square that, right? That'd be 9/4 x squared divided by 2, right? So that would be 9/8 x squared, I think. What you think? Okay? Agreed? All right. Now, all this is then times your dx. Okay? Now, let's combine some like terms there if we can. I'm just going to continue up here, but it's coming from down below. The only x term is 6. This is integral from 0 to 2 of 6x. And then your only constant is 9/2, so that's fine. Now let's combine those two. That will be minus, 3 is 24/8, right? Okay, 24/8, that's a minus 24/8 minus 9/8. That would be minus 33/8. X squared. Okay, this is driving me nuts. Okay, all right, and this is then my dx. All right, goodness gracious, will you quit that? And this is going 0 to 2. I don't know what happened to my 2 up there. Okay, now continuing from there, let's do the integration now. Antiderivative of 6x. Which would be 3x squared, right? Okay, plus an antiderivative of 9/2. And 9/2 x, isn't it? Okay. And then minus, and what would that one be? Three, and the 3 will go into 33 11 times. And that would be 8 in the denominator and an x cubed here. Okay. And that's evaluated from 0 to 2. Okay. All right. So let's do that evaluation. 2 squared is 4 times 3 is 12 plus 9, right, minus 2 cubed is 8, right? So that would be minus 11. And then when you subtract the zeros, nothing comes out, right? So let's see what we've got then. That looks like 10. 9 plus 2, 12 plus 9 is 21, minus 11 is 10. Okay. Whoa, look at that. That's what they got to. Good for them. All right. Now, That's how I chose to do it. Let's see if they chose to do it any differently. This certainly works. Let's see if they did it any differently. All right, to erase. Any questions before I erase? Okay. By the way, Davis, we are in Chapter 14, Multiple Integration, 14.4, which is Center of Mass and Moments of Inertia. We're doing example 1 at the bottom of page 998. Okay. So let's erase this ink if I can get. Okay, it erased finally. All right, as shown in this figure, the region has the boundaries x equals 0, y is equal to 3, and y is equal to 3 has x, or x equal 2/3 y. So you could do this either way you wanted to. We chose that way. Okay, not that it really matters, but we did. Now, and by the way, I couldn't do this very well. They did it sort of okay. Your densest is up here, so that's a little bit darker. Least dense is down here because that's actually zero density at this point here, and it's getting more dense as you go that way. Now that doesn't really mean a lot, except that just shows you do have variable density, so you do have to include the density in there. And your density is 2x plus y. Now, that's the setup. Let's see what your integral is. The mass of the lamina, M, is the double integral over the whole region R of your density function, 2x plus y, times your dA. The dA could either be dx dy or dy dx, just whichever one you want to do first or last, okay? So, they did it the opposite way from what we did, which is fine. It's perfectly fine. They did their dx's first, and they used the second form, which is 0 to 2y, 2/3 y. If you go back here, you'll see, or x equal 2/3 y. So now what they're doing is this one, and they're going from this one, 2/3 y, to 0, and then going 0 to 3. Which has the advantage of having another 0 in there, which makes it maybe a little easier, but I thought the other was maybe a little easier to see, come up with our equation. But anyway, so they did it this way. Perfectly fine to do it that way. All right, and when they do that, they first do the integration with respect to x. So this will be x squared plus yx. That's a little bit simpler than what we had, evaluated from 0 to 2/3 y. These are x values here, so you put these things in for the x, okay? And therefore, you will have put this in for x, that gives you 4/9 y squared plus, I'm sorry, doing the dx first. So this is first going to be x cubed over 3 plus x squared y over 2. So they skip so many steps, it's pathetic. Okay? Yeah. Okay. Let's fill in the gaps here a little bit. No, wait. No, I mean, I'd already done the integration. So yeah, they're right. They're plugging in these values. So it's integral from 0 to 3 of 4/9 y squared plus, and plugging in that for the x, because again, these are x values. Okay? That would be 2y squared over 3. Okay? And you evaluate, okay, dy. Okay? Now, when you add those two together, you got a common denominators. this would become a 9, and this would become a 6. Multiply numerator and denominator by 6. So that's where you got your 10/9, and you pull those on the outside, and then what you got is y squared. Okay? Factor out the 10/9 on the outside, y squared on the inside. Okay? And then you do that, and that's going to be 10/9, and this will be y cubed over 3, evaluated from 0 to 3, and that would be 10/9 times 27 over 3 would be 9 minus 0, and that gives you 10. So the calculations were a little easier that way, but we got the same answer. Does everybody see how we got that one? How they got it? They skipped some steps, and I tried to put those steps in there. What they skipped was you put in, instead of the x, you put in 2y over 3, which would be 4y squared over 9. That's what this is. That's the y there. The integral from 0 to 3. And this one would be, for the x, 2y over 3. And that would be 2y squared over 3. And that would go here. So here you have 4 over 9, 2 over 3. So you need to get this in terms of 9. So multiply that by 3 and this by 3. 2 times 3 is 6. 3 times 2 is 6. 3 times 3 is 9. So you get least common denominator. Then you add these two together. 4y squared plus 6y squared is 10y squared over 9. So factor out the 10 over 9. Leaving the y squared here. 10 times the root of that would be y cubed over 3. Evaluate that to 0. You got it. 27 over 3, which is 9. And the 9 cancel out. 10. All right. Does that make sense? Let me erase my writing there so you can see how they finish it up exactly like we did. And that gave you 10. Okay. Any questions? Does that make sense? Okay. In this figure, note that the planar lamina is shaded so the darkest part corresponding to the densest part, that's near 2, 3. The lightest part is the least dense part. In fact, it goes to 0 at 0, 0. Okay? That's just their drawing. I can't draw it that way, so I'm glad they did. Now, they're skipping example 2. So let's us do example 2. All right, we'll do it right here. Find the mass of the lamina corresponding to the first quadrant portion of the circle. X squared plus y squared is equal to 4, where the density at point xy, rho of xy, is proportional to the distance between the point and the origin. Okay? Where the density is proportional to the distance between the point and the origin. Okay? So that would be some proportionality constant k times the square root of x squared plus y squared. Okay? That's the distance from the origin. But we do know that the square root of x squared plus y squared, that's equal to 4. Okay? So then this would be 2k. Because x squared plus y squared is 4. Now, did I do that too soon? Perhaps. Okay, so let's not do that quite yet. We may come back and see if it makes any difference, but we'll do it the way they do. Okay? So that's the density. K is a proportionality constant. Now, here's a picture of what we're doing. It's this circle of radius 2. This is a really ugly circle. Okay. Let's see if I can clean it up some. I have a feeling it's going to erase it all. Sorry about that. Yuck. Okay, one of those has got to be better than the others. Get rid of that one and that one. And that one. And maybe that one. Okay. All right. Now, the least density is down here, and the greatest density is out here. Okay, now I can't draw as pretty a shading as they do, but you got the general idea. Now, again, it really doesn't matter which order you do these, okay? But if your final d is going to be your dx, which we'll let that be, then your initial, you're going from y is equal to the square root of 4 minus x squared that you get from solving that one, and then you're going that to 0, and then your x's are going from 0 to 2. Okay? So, your mass now is equal to the double integral over this region R of your density function of K, and I'm going to bring the K on the outside because it's just a constant. There's no reason to keep it inside. And this will be x squared plus y squared to the 1/2. That's how I prefer to write it. And then you're going to have your dy is first and your dx is last. Okay? Because the x's are going, the y's are going from y is equal to 0 up to y is equal to square root of 4 minus x squared. So then your mass here will be your constant proportionality times, this will be your dx is going from 0 to 2, and then your y's are going from 0 to the square root of 4 minus x squared, because that's what this y is equal to. Then you'll have your x squared plus y squared to the 1/2 power not there? Oh, I see. Okay. Good to have you back. Okay. dy dx. Okay. So this will then be k. Your last integral will be from 0 to 2. Let's do the first integral. Okay. Now, in both this and this rendition, this is far, far, far easier to do these in polar coordinates than in xy coordinates. Okay? So, how are we going to make that change? This will be this is just going to be r squared. So in other words, r is equal to 2. That's what we've got drawn here. Okay? And your density function is going to be k times r, because the square root of r squared is r, and we're only going to deal with positive r's. Okay? Now, so I think I'll go back and recreate this because I don't have enough room, since we're not going to use these. Oh, I might need that. Okay. Okay. Your if you remember from polar coordinates, is r dr d theta, though we can change the order around some if we need to. Okay, so I'm going to take these limits off too because we're dealing with something else. Okay, now I don't think we have to mess with anything. We're going, if we do them in this order, your d theta is going from 0 to pi halves, and your r is going from 0 to 2. So I don't think there's anything we have to do there. Your rho is going to be k times r. Okay? And again, oh, we don't need the k inside, it's on the outside, so let's take it out. And r times r is just simply r squared. Wait a minute. My pen's not doing right. So this will be r squared d r d theta. See how much simpler it is in polar coordinates. Okay. So let's do this one. That's going to be k times the integral from 0 to pi halves. We'll come back and do that in a minute. What's the antiderivative of r squared dr? R cubed over 3. Okay, and that's evaluated from 0 to 2. And then we'll do our d theta later. Okay, so let's plug in first what we've got here. K times the integral from 0 to pi halves. And when you plug in a 2, what's 2 cubed? 8 thirds. And then that would be, and the 0 gets you nothing, so that would be d theta. Okay? So we can pull out the 8 thirds times your k, and what's the antiderivative of d theta? Theta. And that theta is evaluated from 0 to pi halves. Okay? Bless you. Okay? And when you plug in the 0 there, plug in the pi halves for your theta, you're going to get 8, okay, you're going to get 4k pi, or 4 pi k over 3. When you plug in the pi halves there, the 2 will cancel out 8 and give you 4. And then when you plug in a 0, you get 0. Okay? That is a 0 down there. It's an ugly looking 0. But I can't get it. Look at that. I don't know what it's doing. This system has been really weird today. Okay. So 4 pi k thirds. 4 thirds pi k, or whatever you want to call it. Okay. And that's exactly what they got in the book. Rather strange system. Far better to go with polar coordinates on that. All right. That was example 2. Let's move on to moments and centers of mass and center of mass. Now, today I'm running out of steam here. I had a treatment on Friday and I haven't quite recovered from it yet, so I'm sort of running ragged. For a lamina of variable density, like we were just dealing with, moments of mass are defined in a manner similar to that used for uniform density case. For a partition delta of a lamina corresponding to a plane region R, this is your plane region R, okay? Consider the ith rectangle, which will count as that one there, of one area delta A sub I. So this area right here is delta A sub I. It's shown in this figure. Now, it didn't quite identify everything here, but basically what you got is a partition that you have a bunch of these rectangles here. We're taking that one, the ith one, okay? Now, this is x sub y here, y sub I there, okay? And this will be the ith rectangle there, called R sub I, okay? Now, this is not going back and bringing you up to speed, it's just talking about it, okay? This little rectangle here has some mass, and that's what they're just calling mass. Now that depends on its variable density, and it depends on its location, because that's what it varies by. So it has some mass. And the mass of this times the distance from the x-axis, which would be y sub I, that gives you your moment with respect to x. It may be hard from where you're reading to see, but that's m sub x. The moment with respect to y would be the distance from the y-axis to here, and that would be your x sub I times that same mass, whatever that mass is at that point right there, of that little rectangle there. Okay, now, you might say, what's variable density, how can we say, ultimately we're going to dy and the dx's both go to 0, so it really doesn't matter. We'll just use a representative amount there, okay? So this is your moment with respect to x, moment with respect to y, and I really personally don't like using the moments. I'd rather just use these ratios, this product here, rather than the moments. They love to use the moments. Okay, so anyway, that's what we've got. Now, what we're going to do next is do your integration. Assume that the mass of R sub I is concentrated at one of the interior points, x sub I, y sub I, which is that dot that was in the middle of that rectangle. The moment of mass R sub I, of R sub I, of that rectangle there, with respect to the x-axis can be approximated, and this is what they had there. The mass times y sub I, that's what we had, moment of mass with respect to the x-axis. How far above the x-axis is y sub I times its total mass. Well, what's its total mass? That's approximately rho of xi yi times your delta A sub I, okay? So this is your variable density, and that's your delta A sub I, okay? Now that's all multiplied by your distance above the, or distance from the, above the x-axis. Similarly, the moment of mass with respect to the y-axis can be approximated as this. That's what they had at the bottom of the last slide, which is your density times your area times your x sub I. That's this part, okay? Now, goodness, I'm running out of steam. By forming the Riemann sum of all such products and taking the limits as the norm of your delta, that's your maximum diagonal distance of your largest rectangular area, delta A, approaches 0, so it means they're all going to 0, you obtain the following definitions of moment of mass with respect to the x and y axis. Okay? So the moments and the center of mass of a variable density planar lamina. If your rho is a continuous density function of the planar lamina R, the moments of mass with respect to the x and the y axis are as follows. The moment with respect to the x will be the double integral over that region R of your y. Remember, that's your distance. The moment with respect to the x-axis, this way, then your distance y is going to be how far it is above the x-axis, and then this is your density function, and there's your area increment, okay? And the moment with respect to y, the y-axis, that's going to be your x value, double integral over the region R, times your density function, times your dA, which is having to do with dx and dy. If m is the mass of the lamina, which we were just doing before, then the center of mass is your x bar, y bar, where the x bar is your center of mass with respect to the y divided by m, and the y bar is the center of mass with respect to x. The moment, I'm sorry, not center of mass, the moment with respect to x over m. If R represents a simple plane region rather than a lamina, then the point x bar, y bar is called the centroid of the region. Okay? A simple plane region rather than a lamina, then that would be the centroid. Now, what I've always heard is the centroid refers to if you have uniform density as opposed to variable density. They're not saying that now. It seems like I've always seen that as a condition. For some planar laminas of constant density rho, now we're saying that, you can determine the center of mass or one of its coordinates using symmetry rather than using integration. Okay? We'll see that, and hopefully it'll make sense when we do it. All right. For instance, consider the laminas of constant density shown here. These are constant density, not any one part denser than the other. Using symmetry, you can see that the y bar here, okay, now, here's your x-axis this way, your y-axis this way, z-axis this way. There's your lamina. And this one has constant density, okay? Now, your y bar, or the y component of your center of mass, is going to be 0, because uniform density across here, and that means you got as much mass on the left side as you do on the right side of that line. So your y bar is going to be 0. It's got to be somewhere on the, I'm sorry. The y component of the center of mass is going to be the midpoint, which is midpoint between y is equal to -1, y is equal to +1. It's going to be y is equal to 0. So that's the center of mass of that. Okay? Now this one over here, again, if it's uniform density, your x bar is going to be 0. There's as much mass on this side as there is on that side, so your x bar is going to be 0. Okay. Now, what the difference is here, you're on this one, well, your region is going, x is going from 0 to 1 here, and the y's are going from minus square root of 1 minus x squared to positive square root of 1 minus x squared. But who cares about that? The y bar is 0. Here, it's your x is going from square root of 1 minus y squared, minus 1 square root of 1 minus y squared to positive square root of 1 minus y squared. And your y's are going from 0 to 1. So the y bar has got to be 0. I'm sorry. Yeah. x bar. X bar has got to be 0. Okay. So here, and jumping to, to example 3. That's the next one. And this one can be found at larsoncalculus.com for an interactive version of this type of an example. So find the center of mass of the lamina corresponding to the parabolic region. 0 is less than or equal to y, and y is less than or equal to 4 minus x squared. Okay? It's a parabolic region there where the density at a point xy is proportional to the distance between xy, the point, and the x-axis. So in other words, the density is least down here, getting greater as you go up. So that's why the pink is getting pinker as you go further from the x-axis. Okay? So basically, this density is k times y. No x dependence on it at all, just k times y. Okay. Now, there's the curve. Y is equal to 4 minus x squared. That's going to be the boundary of y. Okay. Now, find the center of mass of this. Now, since there's no variation left to right, the only variation is up to down, then you know the x bar has got to be 0. Because there's as much mass on this side as there is on that side. This parabola is symmetric about the y-axis, so it really doesn't matter. Your density is proportional only to how high it is. So that's why you've got a ky. There's no x dependence on that. Which also means the x bar is going to be 0. Okay? The center of mass has got to be somewhere on the x-axis here. Okay. On the y-axis, which is x equals 0. So x bar is equal to 0. All right. I'm so tired. Like I said, I'm running out of steam. It was sort of a tough weekend with the treatment on Friday, so let's move with it. All right. Now, when you're finding the center of mass, you need 3 pieces of information. The moment with respect to the x-axis, the moment with respect to the y-axis, and the total mass. Now, we've already determined the moment with respect to the y-axis is going to be 0. X bar is going to be 0 because it's the same everything on both sides of the x-axis. So we don't have to worry about that any because you know your x bar is 0. That's the moment with respect to the y-axis. Okay? Now, so we just need those 2 pieces of information. The mass and then the y bar. How far up and down from the x-axis is that center of mass? Okay. Now, what you want to do first? The mass or the moment with respect to x-axis? It's up to you. Mass. Let's do mass first. Now the mass is very similar to what we did before. Mass is equal to the double integral over the region R, and this is what we're going to call our region R, of your density function, which is this, ky. I'm going to bring the k on the outside, the y on the inside. I'm sorry? I can't hear you. Oh, yeah, times, okay. It'll certainly be times dA. Perfect, okay. I'm sorry, I couldn't hear what you're saying. Okay, but you got something else in there. No, okay, no. I mean, not for mass. I was doing the other. Okay? So that's what you got. Your dA here. It's going to be your dx dy. Okay? And which way you want to go first. Okay. Since we know y is going from 0 to this, that seems like the first one to do. So this would be k times the double integral. The one we're going to do first is the y from 0 to 4 minus x squared, because they gave that to us basically. And that's going to be y times, and since we're doing this again is y is equal to 4 minus x squared, so we're doing our dy first, and we're then going to do the dx's later. But remember, the dx is the same on right and left, so we can just double that and do the x from 0 to 2. Because the mass on the left is the same as the mass on the right, so we'll just go from here to there and double it. So that's why we're going to allow that one. This one will be going this way. I think we've got it now. Okay? Let's see if we do. What is that? Here's your k. We don't know what the k is. It's just a number k. Okay? The integral from 0 to 2. Okay? What's the antiderivative of y dy? You know it. Second, y squared over 2, evaluated from 0 to 4 minus x squared. Okay? That's what y is equal to. Okay? And then we'll have our dx later, and we'll do that from 0 to 2. And I forgot, I said it, but I didn't write it down. I didn't write my 2 in front, because it's twice the... If you're going from minus 2 to 2, doing 0 to 2, you got twice that mass. Okay. So let's see what we've got. 2k. Let's go on and write it down again. 0 to 2. Okay, let's evaluate. Now this is y is equal to this, to y is equal to 0. So if we're doing 4 minus x squared, what would that be? 4 minus x squared squared. Four minus x squared squared. What would that be? Anybody? Square of the binomial. Okay. 16 minus 8x squared, x to the 4th, and okay, then this is time, and then with the 0 in there, nothing happens, so we're integrating that, the dx there, and this will be 2k times 16x minus ax cubed over 3, x to the 5th over 4, and you evaluate that from 0 to 2. Oh my goodness. I'm sorry. Oh, that's 5. Goodness gracious. The old gray cells ain't what they used to be. I was thinking 5 and wrote 4. I don't know why. Okay. Well, back. Okay. Now, this is just to get the mass, by the way. All right, let's plug in the 2 there. That'd be 2K times 32 minus, say that again, 64 over 3. My hearing's bad, so I wasn't sure I understood that. Plus 32, right? Yeah. Huh? 32 over 5. Okay. Now, going to be a messy number, but it's certainly doable. Least common denominator is 15. So it's 2K and whatever 15 times 32 is. Can someone punch that in real quickly? 480 over 15 minus 5 times 64, 20, 320 over 15 plus 3 times 32 is 96 over 15. Okay. Now I can't read my writing because my pens get like crazy, but we'll get Rachel here first. Okay. All right. Okay, you've already done the math. I can't read my writing there. Did you already multiply by 2K too, or not? Okay. So what did you finally get? 266? 256 with a K or not? Okay. Over 15 times 2K. So this will be 512 over 15 times K. Now, I don't think anything will go out there. And I seem to have made a dumb error somewhere. I see where it is. I've lost my 2 here. See, there's a 2 down there. I just plugged in. Actually, we do lose a 2 because of that. And so we lose it there, and there, and there, and there, and there. So we do leave just 256. So because I was lost down in my writing there, I didn't see my 2. So sure enough, it's 256K over 15. And that's the mass they got. Okay, 256K over 15. Okay. That's the mass part. Now we've got to get the moment part. And remember, the moment that we're dealing with is the moment with respect to the x-axis. So that's going to be the y times this. Okay? Because we already know that the moment with respect to the y-axis is going to be 0, okay? Because there's the same mass on the left as it is on the right, so with respect to the y-axis, it's going to be 0. Sorry, got the hiccups. So let's do the moment with respect to the x-axis, which is your x times, because that's how, I'm sorry, with respect to the x-axis is your y, yeah, times everything else. So this will be, let's see, we don't need the 2 in there anymore, I don't think. So that's going to be k times the double integral over r of y squared dA. Okay? Let me make sure, yeah. Okay? So that's going to be k. I don't know why the pen is not writing. There we go. And it wrote twice in. The integral, and again, I think it's a good idea to do the dy's first, 0 to 4 minus x squared, and then we'll do your now they're doing the dx's from minus 2 to 2, and I'm wondering if that's necessary, or can we just do 0 to 2 and double it? I think we can. Right now I'm seeing no reason why we can't. We'll see if we come up with the same answer. Okay? If we don't, then I blew it. But I think we should come up with the same answer. Yeah. So we'll go 0 to 2 and double it. They didn't do that, but we will. Okay. Okay. The system is incredibly slow. But now it's a y squared, and we're doing the y's first, so dy, because this is y is equal to 4 minus x squared. Goodness gracious. Y is equal to 0. And then the dx is last. Okay. So this will be 2k. Now, antiderivative, and we're doing with respect to y, will be antiderivative of y squared will be y cubed over 3. So I'm going to put the 3 out here. That's what they do in the book, which is a good idea. Going from 0 to 2, okay? And this time we're evaluating this y cubed from 0 to 4 minus x squared. This drives me crazy. Okay. And then we'll do our dx last. Okay. Now we've got to cube that messy polynomial there, which was, remember, that was 16 minus 8x squared plus x fourth, and we're going to multiply that by 4 minus x squared again. Okay? It's kind of like a falling problem, but this is going to be 64. 4 times 16 is 64. Okay? And then we've got a minus 32x squared, and you got a minus 16x squared. So that's going to be a minus 16 and 32. I think it's 48x squared. Okay? Now you got your x to the fourth terms, which is plus 8x to the fourth plus 4x to the fourth is plus 12x to the fourth. Okay? Okay? And then you got your x to the sixth terms, which is minus x to the sixth. Okay, now I sort of did that fast, and I hope I didn't lose anyone in it. This was what we got when we did it before, right here. This one right here, right? When we squared it. Then we multiply it by it again because we're cubing it this time. and then you do the constant terms of 64, and then the squared terms are minus 16 and minus 32, which is minus 48. I hope I did my adding right. And your x to the fourth terms would be plus 4x to the fourth, plus 8x to the fourth, plus 12x to the fourth, and then your x to the sixth terms would be minus x to the sixth. So that's when you cube that one. That's what you get. Okay? So, I'm rapidly running out of room here. So what I'm going to do is erase this up at the top, this part of it, and the answer to that was cubing that. So this is what is going to be inside my integral from 0 to 2. Now, why the integral came out like that, that's not how I drew it. So let me see if I can get that to draw better this time. This is really weird what this is doing. Okay, there we go, or at least part of it. Okay, and this is going from 0 to 2. And out in front of that is 2k over 3. Okay, and we got our dx out here then. Okay, so you tell me what that integral is going to be. Okay, I'll put the 2k over 3 out front. 64x minus over 3. Well, 48, yeah. 48 divided by 3 is 16, right? So that would be minus 16x cubed. Okay. Plus, I hope I'm doing this right. Oh, goodness, I can't. Okay. Plus, and that would be an x to the fifth over 5, 12x to the fifth over 5. And my pen is so slow. And then we will have a minus x to the seventh over 7, evaluated from 0 to 2. Okay, promises to be a really big mess. So I'm going to go back to the front of this line and start doing this. 2k over 3 times. When you plug a 2 in there, that gives you 128, right? Minus 8 times 16. That's 48 again, isn't it? Okay. Plus 32 times 12. I'm not quite ready to do that one in my head. Divided by 5. What does that give you? 32 times 12. What does that give you? Second? 384 over 5 minus, oh boy, 128, I believe it is, over 7. Now, do any of you have one of those calculators that will do fractions? And you can just do the fractions. I don't have to figure out least common denominators. You don't? Okay. You do? Good deal. Thank you so much. Because least common denominator would be 35. Then you got to multiply. Well, you can subtract that and give you 80 times 35. It wouldn't be miserable, but it's still a pain in the neck. Okay. 35 times 3, sure enough, is 105, so that part looks right. Yeah, here, this one here. Just do this part. 80 plus 380, someone tell me what that number is, 4? I think it was, wasn't it?
Yes.
I think it was 384 over 5 minus 128 over 7. Multiply that by 2/3. And what do you get? 2 over 3. Hopefully give me a fractional answer. Got it yet? Okay. Huh? It's a shame to waste this much time just on math, but does it give you an answer? Okay. Huh? Okay. Let me just give you what the book has an answer. I think it's probably close to right. It gives you 4096K. I'm going to write this at the bottom. 4096K over 105. I'm pretty sure that's what we get. Okay? Now, that means your Y bar is going to be this number, 4096K divided by over 105 divided by 256K over 15. Okay, now the obvious things are the K's go out. Okay? Now I'm thinking that the 15 will go into 105. What's that? 5 times, I believe. No, 7 times, won't it? 7. Okay? So the K's go out, and you're left with 4096 over 7, and that's divided by 256. So do 4096 divided by 256. 16, that's what they got. 16 over 7. So there is where you go. 16 over 7 is a little bit more than 2, because 14 over 7 would be 2, so it would be somewhere right about there. Okay? On the y-axis, just a little bit above 2. Okay? And that's what they show here too. Now, for some reason, they lay it down and have a weird orientation of it, but here's what it is. The lemma is symmetric with respect to the y-axis, and the density function is ky, where k is a constant of proportionality. So the center of mass lies on the y-axis where x bar is 0. We determined that right at the beginning. Okay? To find y bar, first, this is what y'all chose to do, to find the mass of the lamina. Now, the only thing different here, we did twice 2k out here, 0 to 2. Other than that, we did the same thing they did, and that gave and they just integrated this and got y squared over 2 going from 0 to 4 minus x squared. We remember we squared that. But you see, we did twice this and 0 there, so if you just keep that in mind, I'm going to go on and make it this 2 and a 0 here, and that would wipe out this and make a 0 there, okay? So, continuing what we did, that would be wipe this out and a 0 there, and then we did that integral, and you got that there, that is wiped out and a 0 here. I'll put the 0 in the wrong place. And then when you plug in the 2, you get k times 32 minus 64 thirds plus 32 fifths. Okay? And that came up with the 256k over 15. Exactly what we got. Okay? It's Matthew, right?
Yes.
Okay. All right. We're in Chapter 14, Multiple Integration, 14.4, Center of Mass and Moments of Inertia, and we're on Example 3, doing the solution here. We just got the mass of the lamina, okay, and now we're going to do the moment of inertia from or about the x-axis. So that was our 256 k over 15, same thing we got. So let's do the other part. And again, we're going to do it slightly different from them. We'll find the moment of inertia about the x-axis. And again, this is going to be proportional about the x-axis, so we're going to put a 0 down here and double here. We're going to pull a k on the outside. So we're going to have a 2k here. This is a 0 there, and we won't have the k in here. Okay? But everything else is the same. Okay? So that's going to be a y squared, and if you do the integral there, and again, we did 2k over 3 with a 0 down here, y cubed, because they integrated the y squared and got y cubed over 3. They put the 1/3 on the outside, the y cubed on the inside. Evaluated that, and then that, sure enough, I think is the number we came up with, and that would be 2k going from 0 to 2. And when you do that, you get 2k here, 0 to 2 there, okay? And then they got 4096k over 115, not 105, okay? Now, putting the moment of mass about the x-axis over the mass, that gives you the y component of the center of mass. So you put y bar is equal to m sub x over m, and that would be those, and you see the k's go out. This goes to 7, and this goes to 16, so it's 16 divided by 7. Okay. So there, the center of mass is x bar is 0, y bar 16/7. They don't show the picture. They do in the book, but they don't here. Why they turned it over and laid it flat, I'm not sure. I don't even know. Okay. Now, this is taking a while. Do y'all have, okay, most of you engineer, pre-engineers? No? What's your majors? Meteorology. Do you know if you need moment of inertia? Do any of you need moments of inertia? You might. I don't know. I'm not an engineer myself, so I don't know. What you think? Yay or nay? You don't think so? Okay. What I'll do is do a quick slideshow of it, but I won't test you on this part. Okay? You can be tested on center of mass, but not the moment of inertia part. So let's just go over quickly what the moment of inertia is. Okay? The moments m sub x and m sub y used to determine the center of mass of a lamina are sometimes called the first moments about the x-axis, that's m sub x, and the y-axis, m sub y. Each case, the moment is the product of a mass times a distance. Okay? So the moment with respect to x is the mass, which is your rho dA, times the distance from that axis. And this would be the mass, rho dA, times the distance from this axis, which is your x. The y-axis would be your x. So that's what your moments are. Okay? That's what we were just doing. Okay? You will now look for another type of moment, the second moment, or the moment of inertia of a lamina about a line. Okay? Not necessarily an axis. In the same way, the mass is a measure of a tendency of matter to resist a change in straight line motion, and the moment of inertia, which is exactly what resisting change is, about a line is a measure of the tendency of matter to resist a change in rotational motion, not in linear motion, but rotational motion. For example, when a particle of mass m is a distance from a fixed line, its moment of inertia about the line is defined as I is equal to m, that's its mass, times the distance from that line squared. Okay? Whereas before it was mass times the distance, now it's mass times the distance squared. As with moments of mass, you can generalize the concept to obtain moments of inertia about the x and y axis of a lamina of variable density. These second moments are denoted by I sub x and I sub y, and in each case the moment is a product of the mass times the square of the distance. So your I sub x would be the double integral over r times y squared rho dx. So you see, just like before, except it's a y squared here. And I sub x is, if this was an m sub x, the first moment, then it would be a y there. Okay? M sub y would be an x there. I sub x, moment with respect to the moment of inertia with respect to the x-axis, y squared there, I sub y would be x squared there. The mass being the same. The sum of those moments, I sub x, I sub y, is called the polar moment of inertia and is denoted by I sub 0. Okay. Now, again, I don't know how much y'all are going to get into this. You might not. I just don't know. But at least you've seen it at least once now. For a lamina of, in the xy plane, I sub 0 represents the moment of inertia of the lamina about the z-axis. Okay? For lamina in the xy plane, I sub 0 represents the moment of inertia about of the lamina about the z-axis. The term polar moment of inertia stems from the fact that the square of the polar distance r is used in the calculation. Okay? So if you sort of go back and combine those two together, the sum of those, this is your r squared. Okay? In polar coordinates. Okay? But it's rather bizarre because you have this still in x's and y's. So this is a bit strange. Okay? And we'll just watch them do it, but we won't do it ourselves. Find the moment of inertia about the x-axis of the lamina in example 3, the one we just did. Okay, from that definition, I sub x, and that's what they're looking for, moment about the x-axis, I sub x. So now this time, I think we can still do twice 0 to 2. Don't know for that for sure, but I think we can. And this will be y squared ky, that was your density formula, dy dx. Okay? So this is going to be ky cubed, but it's going to be 2ky cubed. 2k out here, y cubed in here. So that'll be y fourth over 4. And I'm going to put a 2 here and a 0 down there. Okay? And then you plug this in. Well, now you got to raise this to the 4th power, which is doable, but I'm glad we don't have to do it. When you raise this thing right here, 4 minus x squared to the 4th power, you get 256 minus 256 x squared plus 96 x fourth minus 16 x 6 plus x to the 8 dx. Okay? Now the only difference I would do is do a 0 here, and then if you put a 2 up here, this would be over 2. Okay? Now you might say, what happened there? Well, the over 4 came here. Remember, we had a 2k up here. Now it's k over 2. Okay. Now, doing the integration, 256k, 256 x cubed over, 256 x minus 256 x cubed over 3 plus 96 x 5 over 5 minus 16 x 7 over 7 plus x 9 over 9. Evaluated with a k over 2 here, this goes 0 over 2. And then you plug in those numbers and you get this beautiful looking number. Even worse than we had before, okay? That's the moment of inertia about the x-axis, okay? Now, the moment of inertia, I, of a revolving lamina can be used to measure its kinetic energy. For example, suppose a planar lamina is revolved about a line with an angular speed, omega, which is radians per second, as shown in this figure, okay? So here, these little circles here, that's your lamina, planar lamina, and it's going around here at a speed of omega radians per second, okay? Now, the kinetic energy, E, I would say Ke of the revolving lamina, is 1/2 I omega squared. Now, some of you have done physics already, right? If you have, kinetic energy was 1/2 mv squared if you're doing linear motion. This is angular motion, so it's 1/2 I. The I replaces the mass, and before you use a linear velocity, here you use an angular velocity. So this is very similar formula if you ever need it. On the other hand, kinetic energy of a mass m moving in a straight line, this is what I'm saying, Ke is equal 1/2 mv squared. Okay? So you see the similarity in the representations. So the kinetic energy of a mass moving in a straight line is proportional to its mass, but the kinetic energy of a mass revolving about an axis is proportional to its moment of inertia, not the mass. Okay. The radius of gyration, this is getting way beyond, I think, what most of you will need, but if you ever need it, this is it. And that's called R double bar. I'm not even familiar with that kind of, is of a revolving mass m, moment of inertia I is defined as the square root of I over m. Okay, radius of gyration. If the entire mass were located at a distance r from its axis of revolution, it would have the same moment of inertia and consequently the same kinetic energy. Okay. Oh, man. So what we had before, remember, this was the number we came up with for moment of inertia with respect to the x-axis. This was the center of mass, the moment of just the moment with respect to the x-axis. First moment with respect to the x-axis. Divide those, take the square root, and you get something close to 2.469. Okay. That's enough of that. Okay. My word. All right. Now, homework exercises in 14.4. Again, you're only responsible for center of mass and first moment. So that would be any of the, either 3 or 5. They're both at Calc Chat. 3's at Calc View. 7 or 9, they're both at Calc Chat. 11's at Calc Chat. Any of the I's 13 to 23, they're all at Calc Chat. 13's at Calc View. Either 25 or 27, they're both at Calc Chat. Stop there. Okay? We are not doing radius of gyration. Okay? So, let's move on to, and we'll probably go this a little more in detail than we did that, but, especially toward the end. So let's go to 14.5. Now, just a moment here. Have I just gone way past our normal break time? Do you need a break? You do, okay. So this is a good time to break those. So let's get our slideshow set up. I'll put this on pause. The thing's just acting really strange today. When I do that, then it comes up with that, okay. So, continuing, I'm sorry. Chapter 14, multiple integration. 14.5 is going to be surface area, okay. Now, our objective here is to use a double integration to find the area of a surface, okay. Now, this is going to be hopefully reminiscent of a few things you did back in Cal 2, I believe it was. You know a great deal about the solid region lying between a surface and a closed and boundary region R in the XY plane. Remember, we could do a grid down here, partitioning down here, and then do the height times the area of that partition down there, and that gave you something about the solid region, okay? Now, you know how to find the extrema on R. That's, with your partials, okay? The area of the base of R of the solid, we knew how to do that. We did that earlier. The volume of the solid, that's what I was just describing. And we've also done the centroid of the base of R, okay? Centroid down there, just that base. Now, where are we going from there? In this section, you'll learn how to find the upper surface area of the solid, okay? So how do we do that? Let's begin with consider the surface given by z is equal to some function of x and y, right? Okay, that's the height up here above some function of x and y down here. All right, let's define over some region R, same as we were doing before. Assume that R is closed and bounded, and the f has continuous first partial derivatives throughout that domain, okay? Now, to find the surface area, construct an inner partition of R, just like we did before, of the base down here, the inner partition, consisting of n rectangles, where the area of the ith rectangle, R sub I, is delta A sub I, okay? And that would be delta X sub I times delta Y sub I, as shown down here, okay? Now, in each of those R sub I's, that little rectangle there, let X sub I, Y sub I be the point that is closest to the origin. Why that? Doesn't really matter, but let's be, so that would be the interior point closest to the origin, okay, wherever that might be, okay? At that point, the X of Y, X sub I, Y sub I, Z sub I, so here's this point here, go up to Z, and that would be the one closest to the origin that way. On the surface consists of, at that point, and your Z sub I is your f of X sub I, Y sub I, on the surface of S, construct a tangent plane T sub I. Boy, this is getting sort of strange, isn't it? So here's your tangent plane, here's that surface up there. We're going to do that inner corner there, the one closest to the origin, and we're going to do a tangent plane at that corner, wherever that tangent plane might be. All right? Now, we're going to estimate the delta S sub I to be the same as the delta T sub I. Okay? Now, obviously, delta S sub I is more than delta T sub I, but we can live with that. It's not going to be a lot different, especially if you let your partition get smaller, smaller, smaller. They get closer and closer and closer together. Okay? Now, the area of the portion of the tangent plane that lies directly above the R sub I is approximately equal to the area of the surface area lying directly above S sub I. That is what we just said. The delta T sub I, the area of the tangent plane directly above that partition, is about the same as delta S sub I. Delta S sub I being a little bit larger. So the surface area of delta S sub I is approximated by the surface area of delta T sub I, especially when you let your partition get smaller and smaller and smaller. The norm goes to 0. Okay, to find the area of the parallelogram, delta T sub I, note that its sides are given by the vectors. Now that's your tangent plane up there. They're given by the vectors delta x sub I in the I direction and L sub x, x sub I, y sub I in the k direction. Okay? That's your u vector. That's the vector in the ik dimension, I being this way, k being this way, so that would be your vector in that dimension. Your vector v in the jk dimension would be the one this way, and that would be delta I sub y, delta y sub I j plus L sub y, okay, x sub I, y sub I, delta y sub I k. Okay. Now, you see now why you needed to have continuous first partial derivatives. Okay? Now, here's the theorem we're going by. And frankly, the book is not following, the slideshow is not following the book very well at all here. Okay? Sorry. I know what they're doing now. They're jumping back to something we did back in chapter 11. Okay? But I can't see that in the book here. Here we go. Okay. Where we are, if you're trying to follow in the book, is on 14.5 surface area, page 1006, 1006, about 2/3 of the way down the page, and it says from theorem 11.8, which is back in chapter 11. Okay? That's why it was getting me crossed up, because they're not showing it in the book, but he's showing it here on the slide. The geometric properties of the cross product. Remember that? If u and v are non-zero vectors, which now we're just considering to be, in space, then, and let theta be an angle between u and v. Remember we said these were the parallelograms, so that's the angle between u and v. U cross v is orthogonal both to u and v. Yeah, that's what cross products are. They're always orthogonal to the two component vectors. The magnitude of u cross v is magnitude of u times magnitude of v times the sine of that angle between them. U cross v is 0 if and only if u and v are scalar multiples of each other. Well, if these are in the direction of the x and the y partials, they can't be. So that's not going to be the case here. And the magnitude of u cross v, so here, is the area of the parallelogram having u and v as adjacent sides. And that's exactly what we were saying B's U and V's R. So this is going to be the area of the parallelogram that we're dealing with here. So from this theorem, the area delta T sub I is given by the magnitude of U cross V. And remember how we did that? Now let's go back a slide or two. U is that one, and V is this one. U is delta X sub I, F sub X, F of I, Y of I, then delta X sub I, and V is similar, only delta Y sub ij plus partial with respect to X, delta X sub I, delta Y sub I, delta Y K. Okay? So, to do our cross product, remember how we did I, J, K, and then the one that's first, delta X sub I, it had a 0 component here, and this was the K component. L sub X, X sub I, Y sub I, delta X sub I. The V component, or V vector, was 0 here, delta Y here, delta Y sub I here, and L sub Y and X sub I, Y sub I, delta Y I there. Now, how I usually do this was extend the I and the J one more time here, and then just do your diagonals, okay? But let's just take a look at the diagonal. First diagonal would be 0, okay? The second diagonal, if you put this one here, that would be 0, okay? The third diagonal downward would be this one times that. And that's I do not see how they get a minus sign there. No, I'm sorry. This one times that. Okay. I still don't see how they get the, no, it's K. Yeah, I'm sorry. This one times this one times this one. So that's this one right here. Okay. So that's what you get from the down diagonals. From the up diagonals, your first one is a 0. Your next one is a minus this one, I, because that would be here. That would be the one up here. So minus L sub X, X sub I, Y sub I, delta X sub I, and then this delta Y sub I. And then your next one would be the next one over with your this row here, and that would be minus this times that times J. So this would be minus L sub Y, X sub I, delta X sub Y, that came from this one, and the delta Y sub I came from that one, from the J from up here. Okay. So yeah, that's exactly what they have. They moved them around to have I, J, and K. Okay. Now, that's the cross product. And if you'll notice here, you have a delta X sub I, Y sub I here, here, and there. Well, that's delta A sub I. So that leaves you with minus L sub X, Ij, X sub I, Y sub I, minus L sub Y, X sub I, Y sub I, J, and then you just have your plus K there, because you factored out the delta X sub I. Okay, that's your cross product. The magnitude of the cross product, that's what we're looking for. You just take the magnitude of those, and that's what gives you this. Okay? Because this one's a minus, but you're squaring it, so it's L sub X sub I. Okay? Well, let's go back here. This squared plus that squared plus 1 squared. All times your delta X A. But then you go square root of it, and it comes out. So this is this squared plus that squared plus 1 times your delta. Okay. So the surface area is a summation of all those. And this, remember, this was your delta T sub I. We're saying it's probably the same as that. So what they've done here for some reason, switch the order, move the 1 up front and the f sub x here, f sub y squared there, delta A, and that, so here's the reason I did that, that looks a lot like what we did for surface area of an arc, the arc length is what I'm trying to say, the arc length. And that was very similar to what we had there. So we take this and make it into a double integral, and you get something that looks just like this. This suggests the definition of surface area below. If f and its first partial derivatives are continuous on some closed region R in the xy plane, then the area of the surface S, given by z is equal to f of xy over that R, is defined as the double integral over that region down there of your delta S up there, which would then be, taken from this, the square root of 1 plus f sub x squared of xy squared plus f sub y of xy squared dA, where the dA is dx dy, okay? Or whatever dA you're using. Okay, that was the definition, top of page 1007. As an aid to remembering the double integral for surface area, it's helpful to note the similarity for the integral of arc length, which is what I was saying before. Here's any old length on the x-axis is the integral from a to b of dx. That's the length x, b minus a. The arc length in the xy plane is your integral from a to b. Now, ds, now here this was in a straight line, horizontal x-axis. Length along there is just that. This is a ds, which could be arc length, a curve there. And this is s goes from a to b. And if you, oh, they've been really sloppy here. These are not the right limits for this, okay? So forget that. Just either ignore these limits or put something else in there. But when you do it dx, this is going, the square root, the arc length is going to be the square root of 1 plus f prime squared, because this is just a function of x alone. The square root of that dx is x goes from a to b. The area in an xy plane is a double integral over the region of your dA. That's a lot like this was. Well, the double area of your surface area, the integral of your surface area is going to be the double integral over R of ds, capital S, where that's a surface up there, which is double integral over the region R down here of the square root of 1 plus f sub x squared plus y sub x squared, the root of all that times your dA here, as opposed to, somewhat to your dA here. So this is the sort of shorthand, hopefully help you remind you of what that looks like. All right. So here's example 1. Find the surface area of the portion of the plane z is equal to 2 minus x minus y. Okay? Find the surface area of the portion of the plane z is equal to 2 minus x minus y that lies above the circle. X squared plus y squared is less than or equal to 1. So that's going to be the circle here. Okay? But the portion of this plane here that's above this portion of the circle there. Okay? In the first quadrant, so it's positive x, positive y, positive z. Positive x and positive y, first quadrant down here. That will give you something in the first octave here. Okay, now, just a little bit of reminder here. Z is equal to 2 minus x minus y. That's this plane here. And, of course, when x and y are both 0, your z is equal to 2. So that would be that point there. When your y and your z are both 0, you get x equal 2. That would be there. when x and z are both 0, that gives you y is equal to 2. So there you have the plane that does that equilateral triangle cutting across there like that. Okay? Other things to note is when your y is equal to 0, which is back here on the xz plane, then here is the line z is equal to 2 minus x, and sure enough that would be z is equal to 2 minus x, that would be this line here. And when x is equal to 0, that would be in the xz plane, then z is equal to 2 minus y, that would be this line right here. Okay? So we've got everything we need there. And of course, when z is equal to 0, x plus y is equal to 2, that would be this line down here. Okay. Now, we're not doing all that plane, but just the portion of the plane above this circle here. That region R is x squared plus y squared less than or equal to 1. Okay. So we want the surface area up here of that. Okay? Now, and for some reason, I don't know why my it's not charging well again, and it seems only to do this on this plug. Charges at home, it charges in the office, it doesn't charge here. I don't know why. But anyway, let's do it. So the surface area of a portion of the plane, let's get my pin set up here. Okay? Let's go back and see our formula. Here it is. It's the double angle over the region R, ds, and that would be exactly this thing here. So this would be the, let's see where to put it. Let's do it here. Double region over the region R, double integral over the region R of your square root of 1 plus f sub x squared plus f sub y squared, dA. Okay. Now, that's real shorthand because the other takes so long to write. All right. Now, let's remind ourselves, our dA down here is this part down here, just this part here. So we're doing, this part looks like it would be far easier to do in polar coordinates, but the other part may not be, okay? So that would be r squared is less than or equal to 1. Don't know if that's going to be good to change to that. Let's hold on before we do it, okay? Now this is your function, f, okay, of x and y. Okay, so what we've got to do is f sub x, and what would that be? F sub x. Pretty easy to do. What would that be? Here's your f sub x, is this thing. What is the first partial of f with respect to x? Say again? Okay, no. That's a constant. Partial of that with respect to x is 0. This would just be a minus 1. And the partial with respect to y of xy would be minus 1. Okay? So what we have here is the double angle, the double integral, goodness gracious, of the square root of 1 plus 1 plus 1, square root of 3. I don't need that big a square root, do I? Okay. This almost looks like it's too easy. Okay. dA. Okay. Now, let's deal with the dA. That's not the district attorney. Okay. It really doesn't matter which one you do. dx, dy, dx, it doesn't matter. If you did dx, dy, then this will be x equal 0 to x equal the square root of 1 minus y squared. Okay? And this would be going 0 to 1. Okay? Now, square root of 3 is just a constant. Bring it on the outside. So we have the square root of 3 times the integral from 0 to 1. We'll do that later. Okay? And frankly, let's just do this the easy way. Let's not even mess with the limits yet. Okay? Let's just keep it over the region R. But the region R is just a quarter of a circle, right? That's what your R is. That quarter of a circle. Okay? Now, so it's the region R of the area of that circle. dx, well, let's just call it dA. There's no reason to get even x and y's in there. Okay? And what's the area of the region of a circle? Of a quarter of a circle? Of radius 1. Radius 1. It's the area of a quarter of a circle. Radius 1. Anybody know? What's the area of a full circle? Pi r squared. But r is 1, so that would be pi, right? So a quarter of that would be pi over 4. So what do we have? This would be root 3, pi root 3 over 4. That's all there is, folks. Now, they wrote root 3 pi over 4, but it's really so much easier. I mean, I like to put the radical at the end, so you don't think the pi is under the radical. So I like it that way. They like it the other way. Doesn't matter. That was way easier than what you probably thought it was going to be. I bet you this next one will not be. But anyway, let's see how they do it first. Okay? So let's erase my ink and go, oh, okay, I didn't need to do that. Note that your f of xy is that surface up there, which is 2 minus x minus y. So the partial of alpha of this thing with respect to x is just minus 1. And the partial of this thing with respect to y is minus 1. Both of those are continuous on the region R, the entire region R. Everything's continuous there. Okay? So the surface area is given by, surface area is the double angle over R of the square root of 1 plus this thing squared. That would be minus 1 squared is 1 plus minus 1 squared is 1 dA. That's the formula for the surface area. This is real easy. So this is the double angle over R, double integral over R of the square root of 1 plus 1 plus 1. That's the square root of 3. And you can actually pull that on the outside and do square root of 3 times the double angle over R. But what is a double angle over a region R of an area of a quarter of a circle? Well, that would just be the area of a quarter of a circle, which is the area of the region R, which is a quarter pi, because it's a radius 1, pi fourths, so it's root 3 times pi fourths, which is root 3 over 4 pi. Now, the reason I don't like to write it this way, especially in my sloppy writing, if I get that line a little too long, then I don't know whether the pi is under that radical or not. Now, this is pretty obviously it's not. If you put pi in front, there's no question that the pi is not under the radical. So that's why I wrote it my way. But that's just how I like to do it. All right. That, folks, is the only example they show in this section. Let's us do a few more. If we have time. Yeah, we do have time to do at least one more, hopefully. So let's back off and do example 2. Now, if you want to, you can go to larsoncalculus.com for an interactive version of example like example 2. Okay. Find the area of a portion of the surface, and here's the surface, f of xy is equal to 1 minus x squared plus y, that lies above the triangular region, sorry, that lies above the triangular region with vertices of 1, 0, 0, 0, negative 1, 0, and 0, 1, 0. Okay, now, I guess we need to draw a figure since they're not going to provide us one. Okay, now, my three-dimensional drawings stink. I'll admit that 100%. This is your x, this is the y, and this is the z. Okay? Now, 1, 0, 0 would be 1, 2, oh wait. Everything is 1 unit, so let's just get on out here. Let's call this 1 unit this way, this 1 unit this way, and this 1 unit that way. Okay? Now, 1, 0, 0 is right there. 1 on x, 0 on y, 0 on z. Oops. Minus 1 on y is here, so we're going to, this is 1, 0, 0. This is 0, minus 1, 0. 0 on x, minus 1 on y. Okay, here's your, so I'm going back this way. And then this is 0, 1, 0. I can't write. Yuck. Okay, 0, 1, 0. So basically, it's this triangular region here on the xy plane, okay? And we're doing the area of a portion of the surface that lies above that triangular region, okay? And this is the surface there. So, let's just pick a few points here. When x is equal to 1, you have 1 and y is equal to 0, so it's this point right here. You have 1 minus 1 plus 0. So your z is 0 right there, okay? Let's pick this point over here, okay? 0 minus 1, 0. You have 1 minus 0 plus or minus 1. So 1 plus 0 or minus 0 plus or minus 1. That's a 0 right there, okay? Well, let's pick this point over here. 0, 1, 0. 1 minus 0 plus 1, because that's a plus 1. So up here, you are at a value 1 here. So basically, this is the region we're talking about. It's directly over this triangle down here, but it's going up here. It coincides here, and then it's going up here and there. Okay? kind of an ugly drawing. There's a little bit of a problem with it in that it's not flat here like I drew it, because this is in between these points here. This is actually parabolic here, okay? Because you see in between there, like where x is, say, 1/2 and y is -1/2. If you plug this in here, you get y minus 1/4 plus, or minus 1/2. That would be minus 1/4. So you see this is a little bit elevated. So it's basically a sloped surface like this, okay, going up there, okay. The drawing doesn't have to be pretty, thank goodness. Let's just deal with it though, okay. And let me make sure, I think I drew that wrong okay. Let me erase this. I got this point wrong. So I'm going to need to redo my, oh, yuck. Okay. Okay. When I plugged in this f of x, y, and when you put in a 0, 1 there, you get a 1 minus 0 plus 1. That's a 2 up here. So that is at this angle 2 here. Okay. So it goes to here, to there, and this is the curve here because there. Got that better. Okay. That's the surface we're dealing with. The surface over this triangle down here, done by that, and it's a curved surface because of the x squared. Okay. What a mess. All right. Now, what's the question? Find the area of the portion of the surface that lies above that triangular region. Okay? Well, what we need to do, the area of the surface, S, is equal to the double angle over R, and this is your R down here, okay, of this function, well, the square root of 1 plus f sub x squared plus f sub y squared dA, right? Now, what we need to do here is the double integral over the region R of the square root of 1 plus. Now, what is f sub x squared? F sub x. The partial of this f with respect to x. Minus 2x, right? But we're going to square that, so it's going to be plus 4x squared, right? Okay, and what's the partial of this f up here with respect to y? 1. So that's going to be plus another 1. Okay, and then we're going to have our DA, district attorney. Okay, now what this gives us, I'm going to come over here, the double angle over this region R of the square root of 2 plus 4x squared, dA. Okay, now the dA is going to be some dy dx, and how is going to be the best way to do that? Okay. My gut feeling you're going to have two integrals, well, not quite two integrals. two things one way or another. Okay, if you did this line here, this line right here, that's where z is equal to 0. And where z is equal to 0, and this is your z here, you'd have x squared minus y squared is equal, x squared minus y is equal to 1. Now, that's not what we want. Oh, no, this is what I want. I'm not looking at this one. Okay. Now, this line here and this line there, you might say your y-intercept here is 1, and your slope here is going from change of y over change of x. That would be a minus 1. So this would be, this line here is y is equal to minus x plus 1. This line over here is your y-intercept is minus 1, and your slope here is minus 1 over minus 1, which is plus 1. So this is y is equal to x minus 1. This one is y is equal to minus x plus 1. This is y is equal to x minus 1. Okay, now, if you were to do if you do it this way, you're going from y is equal to this one to that one, okay? And then your x will be going from 0 to 1. So let's see if we can set that up to work here. That would be the double integral. Now here's your interior. I'm real tempted to pull out a root 2, but let's not. I think I will. Square root of 2, get that on the outside. What you have left here is 1 plus 2x squared. Okay? If you pull out a root 2, that's what you're going to have. Now, and what we were going to do is our dy's first and dx is last. Okay? The dy is going from x minus 1 to minus x plus 1. I hope I'm doing that in the right direction. And your dx is going from 0 to 1. All right. Now, now they did 1 minus x minus 1 to 1 minus x. Same type deal. And this is a messy integral. I knew it was going to be. That's why I was trying to find some simpler way of doing it. And basically, you need to go to a formula table and pull it out. And sorry about that, but that's what we've got to do. But I've set it up. I pulled out a root 2. They didn't. But the rest of it is basically history. The first one is a piece of cake because there is no y in there. So that would be root 2, an integral from 0 to 1 of, and we'll pull out the square root of 1 plus x squared, or 2x squared here. okay, and that's all outside this integral, and we're basically doing y evaluated the way they write it is x minus 1 to 1 minus x, which is the same thing I did, but they just write it differently, and then a dx. So that one's not too bad. It's the square root of 2 times the integral from 0 to 1 of the square root of 1 minus plus 2x squared, okay? And then you evaluate this from 1 minus x minus an x minus 1, which would be minus 1 minus x again, okay? And you could put that in parentheses if you wanted to. And this is square root of 2, I made that too big, times the integral from 0 to 1 of that's not right. I think that's a plus there, not a minus. Yeah, that's a plus. I doubled my, okay. It's 1 minus x minus an x minus 1. So you've got yeah, it becomes a plus. So I'm going to bring a 2 here, and you got 2 of those. So this is the square root of 1 plus 2x squared dx. Now, that's not a particularly pretty integral to do. You can do it with a trig substitution, but like they say, go to Appendix B, Formula 26, and the power rule, and you do all that, and you come up. This is really gripes me. They put such complicated integrals here so early in the game. Got to find my tables here. Okay, it must be before that. Oh, I think I have this piece of paper at it. Yeah, there it is, the integration table. They say number 26, I mean 26, I think it was. Formula 26. Yeah. And they just plug in and go, and we've set it up right, we've done it right, it just becomes really a pain in the neck to actually do the integration. But if you do, I'm going to move my page over there so I'll be on the right page when I go back to it. I just don't have enough room to even work it out. But that integral in the back is the square root of u squared plus or minus a squared du. Well, our u squared is root 2x, okay? That's our u. Our a is 1. So if you plug that in and do that, you come up with exactly what they get as the solution, which is a real huge pain in the neck to write all that out, but it comes down to being something about 1.681, which is sort of a reasonable seeming answer. Not a very large amount, and that's the surface area over that. I just don't have room on the page to do all that, to write it all out. You can go to larsoncalculus.com and see exactly how they step through that. Please do it. That's the only way to do that. The next example, example 3, is a paraboloid. Well, we're not going to have time for example 3, so I think we're going to have to stop there. Okay? Now, here's the thing to decide what to do. We're going to pick up with example 3 next. Okay? Let me put this in place. Now, we're almost through with surface area, so we'll do that. Then we'll get into triple integrals and applications, and that is a fairly long section. Okay? We'll do 14.6, and what I think we'll do is maybe do a slideshow of 14.7 and 14.8, again, just a slideshow. And that will be it, I think, for the term. If we have a chance, after the slideshows are over and still have a little bit of time, Chapter 15, again, we'll do sort of a slideshow of it, but I want you to be at least exposed to vector fields. They're kind of a pain in the neck, but I think you'll be using them in your areas of study if you're a pre-engineer. I can't say that for sure. Some might. Are any of you mechanical engineers? No? How about, goodness, who else would be using this? How about aerospace? Well, maybe you don't need that. We'll determine. And if we don't need that, I do want you to be exposed to line integrals. Okay? And we will at least do that. But you won't be responsible for it on the test. So what I'm going to try to have is the test ready for you next time. I can't swear that I will because we got this huge hearing tomorrow that's going to eat up most of the afternoon. And if I don't have a chance to do it tomorrow, I'm not going to be able to get it done until Thursday. And then what I will tell you, if you want to come in and pick up the test on Thursday, you can have the weekend to work on it. Otherwise, you can pick it up Monday. And I'm going to try to keep it fairly simple so you can get it done next week. Okay? All right. Good deal. This is getting a little ragged at the end, but this is how terms go sometimes. Any questions?